Now next topic of calculus is that is your continuity. Continuity is from the word continuation. So for example, if we are going from home to workplace and without any break, if we straightway go there, that means that is the, you can say, dictionary meaning that is we are going continuously from home to workplace. So similarly, if the graph of the function does not have any breaks or jumps, then we say that the function is continuous. Once again, that is, if the graph of the function does not have any breaks or jumps, then we say that the function is continuous. Now what do you mean by that? So graph is like this. So you can say that from A to B, this function is continuous function. There is no break, no jumps, that means the function is continuous. Now then, what is going to be the graph of the discontinuous function? So for example, you can see here, now first of all, let's say if we plot the graph of y is equal to 1 over x. This is the function here. Now you can see here, this is your rectangular hyperbola. So the graph of this function is like this here. So x's, that is your x-axis and y-axis, are the asymptotes of this function. You can see that at x is equal to 0, this function is discontinuous here. It is not continuous here. So this can be the graph of the discontinuous function. Furthermore, if I plot the graph of y is equal to tan x, you can see here this is 0, this is 90 degrees, this is 180 degrees. So this is your pi by 2 point here. Now if I plot the graph of tan x in the first quadrant, it goes this way, and in the second quadrant it goes this way. You can see that this function is not continuous, or the graph is not continuous at the point x is equal to pi by 2 here. Further, let's say if I plot y is equal to 1 over mod x, now very easily you will be able to compare these two graphs. Here this is the graph of y is equal to 1 over x. Now I am going to plot the graph of y is equal to 1 over mod x. You can see that the graph of 1 over mod x is like this. So again you can see here this function is discontinuous at x is equal to 0, because there is a break at the point x is equal to 0 here. So this is going to be the graph of the discontinuous function here. Then how to plot the graph of continuous function? For example, trigonometric function y is equal to sine x. You can see that this is 0, this is pi by 2, this is pi, this is 3 pi by 2, and this is 2 pi here. Now this value is 1, this value is minus 1. So this is your sine curve. You can say that this graph is continuous. There is no break, no jump. So hence this is going to be the graph of the continuous function here. Now next is, what do you mean by continuity? So a function fx is said to be continuous at a point A if, that is your limit x approaches to a, fx is equal to f of a. That is, if the limiting value of the function at a point is same as the that is your functional value at the point, then we say that the function is continuous. This is your limit here. So that is, if left hand limit is equal to the right hand limit is equal to the value of the function at a point, then we say that the function is continuous. That is, if limit x approaches to a negative fx is equal to limit x approaches to a positive fx is equal to f of a, implies fx is continuous at x is equal to at a point a here. Now, which means that if the limit of the function does not exist, so you cannot make the function a continuous function. That is, for example, this was the graph of the function. Since the limit of this function at x is equal to 0 does not exist, how can you make this continuous? Now, this is the graph of the function in which limit of the function exists, but you cannot define the function at is equal to 0. Since it is not defined at x is equal to 0, so how can you make this function continuous? So therefore, for function to be continuous, all these three conditions should be satisfied simultaneously. That is, limit should exist and it should be same as the value of the function at a point here. Now next is, what do you mean by removable discontinuity? If limit x approaches to a fx is not equal to f of a, then we say that function has removable discontinuity. How can you remove this? We can remove this by having the value equals to the functional value at the point. Then we can say that that is your discontinuity is removed and the function is now continuous here. Now next is, what do you mean by non-removable discontinuity? If limit x approaches to a negative fx is not equal to limit x approaches to a positive fx, then we have, that is your non-removable discontinuity, because you cannot remove this discontinuity because limit of the function does not exist. So the condition for the function to be continuous is that limit should exist and should be same as the functional value at the point here. Now, one by one, we will discuss all these questions or the applications of continuity here. So, first is discuss the continuity of the function fx is equal to mod x over x for x not equal to 0 and is 0 when x is equal to 0. So we all know that this is your signal function here. Now left hand limit, now at x is equal to 0, left hand limit is limit x approaches to 0 negative mod x over x. Now can this be written as minus x over x? Because when x is less than 0, the value of mod x is minus x. So this is equal to minus 1. Right hand limit. Now this is equal to limit x approaches to 0 positive mod x over x. You can see here this is your limit x approaches to 0 positive x over x. This is plus 1. Because when x is positive, mod x is x here. As left hand limit is not equal to the right hand limit, therefore discontinuous at x is equal to 0. And this is your non-removable discontinuity, because you cannot you can never make this function continuous at x is equal to 0. We all know what is the graph of this function. It is, now this point is 0, 1. The point, this value is not included. This is 0 minus 1. You can see here this is discontinuous at x is equal to 0 because limit of this function at x is equal to 0 does not exist. Now next is show that fx is equal to e raised to power 1 over x minus 1 upon e raised to power 1 over x plus 1 when x is not equal to 0 and is 0 for x is equal to 0 is discontinuous at x is equal to 0. Now we have to discuss the continuity of this function at x is equal to 0. Now that means again first we will be finding the left hand limit, which is your limit x approaches to 0 negative e raised to power 1 over x minus 1 over e raised to power 1 over x plus 1. As x approaches to 0 negative, 1 over x approaches to minus infinity. Now e raised to power minus infinity is approximately equal to 0. So that is, as x approaches to 0 negative, 1 over x approaches to minus infinity and e raised to power minus infinity approaches to 0. So therefore this is equal to 0 minus 1 over 0 plus 1, which is your minus 1. Now what is the right hand limit? So this is your limit x approaches to 0 positive e raised to power 1 over x minus 1 over e raised to power 1 over x plus 1. So as x approaches to 0 positive, 1 over x approaches to positive infinity and hence e raised to power infinity approaches to infinity. So that means this will come out to be infinity upon infinity form, which is your undefined form. To remove this form, we will take e raised to power 1 over x common from the numerator, 1 minus 1 over e raised to power 1 over x upon e raised to power 1 over x into 1 plus 1 over e raised to power 1 over x as x approaches to 0 positive. So that means it is 1 minus 0 upon 1 plus 0, this is equal to 1. Since left hand limit is not equal to right hand limit, therefore this function is discontinuous at x is equal to 0. So again you can never make this function continuous at x is equal to 0 because the limit of the function at x is equal to 0 does not exist. Now next is let's say function is given by fx is equal to half minus x when x belongs to 0 to half, is 1 when x is equal to half, is equal to 3 by 2 minus x when x is greater than half but less than equal to 1. So we have to discuss the continuity of the function at x is equal to half. Whether it is written or not, we will always check the continuity of the function at the breaking point where the function breaks. Function breaks at x is equal to half. So we will discuss the continuity of the function at x is equal to half. So what is the left hand limit? Left hand limit is limit x approaches to half negative 1 by 2 minus x. Is that half minus half, which is 0? Now right hand limit. Right hand limit is limit x approaches to half positive 3 by 2 minus x. This is 3 by 2 minus 1 by 2, which is 1, and f of half is equal to 1. Since these two are not same, therefore the limit of this function does not exist. Since the limit does not exist, hence this function is discontinuous at x is equal to half, but is right continuous at x is equal to half because these two values are same here. Sometime you might be asked whether it is left continuous or the right continuous. Yes, we can, looking at this, we can say that this function is continuous at x is equal to half from the right hand side. Now next is discuss the continuity of the function fx is equal to modulus of x minus 1 plus modulus of x minus 2 at x is equal to 1 and x is equal to 2 here. So we have to discuss the continuity of this function at x is equal to 1 and x is equal to 2. So before discussing this, first of all, we should know how to define this function, how to define the modulus function, and this is also going to be helpful in plotting the graph of this function. Now, first case is, we will consider the case when x is less than 1. Second case is when x belongs to 1 to 2. And third case is when x is greater than or equal to 2. When x is less than 1, we know that mod of x minus 1 is minus of x minus 1. We know that mod of x minus 2 is x minus 2 if x is greater than 2. For all those values of x less than 2, it is going to be minus of x minus 2. Similarly, when x is greater than or equal to 1, this is going to be positive. But for less than 2, this is going to be negative here. And for all those values of x greater than or equal to 2, it will be x minus 1 plus x minus 2 here. So how do we define it? This is minus x plus 1 minus x plus 2 for x less than 1. It is x minus 1 minus x plus 2 for x belonging to 1 to 2. This is 2x minus 3 for x is greater than or equal to 2 here. So which means that this is equal to minus 2x plus 3 for x less than 1. It is 1 for x belonging to 1 to 2 and 2x minus 3 for x is greater than or equal to 2. So now we have been able to define this modulus function at the points 1 and 2. Now first I am going to check the continuity of the function at x is equal to 1 and x is equal to 2. Then graphically we will see how the graph of this function is going to be. Now, first is continuity at x is equal to 1. Left hand limit. What is that? Limit x approaches to 1 negative minus 2x plus 3. So this is minus 2 into 1 plus 3 which is equal to 1. Now right hand limit. Right hand limit is equal to limit x approaches to 1 positive, that is your 1 because this is your constant function which is equal to 1. So what is f of 1? Functional value at 1, that is also 1 which is 3. So from first, second and third, left hand limit is equal to the right hand limit is equal to the value of the function at the point x is equal to 1, which clearly shows that this function is continuous at x is equal to 1. Now similarly, continuity at x is equal to 2. Now left hand limit, this is equal to limit x approaches to 2 negative 1 which is equal to 1. Right hand limit, that is your limit x approaches to 2 positive 2x minus 3 which is your 2 into 2 minus 3, that is also equals to 1. Now functional value at 2, this is your 2 into 2 minus 3, that is also equals to 1. So from 4, 5 and 6, left hand limit is equal to the right hand limit is equal to the value of the function at the point, so which shows that this function is continuous at x is equal to 2. Now we have been able to see that this function is continuous at x is equal to 1 as well as continuous at x is equal to 2. So how the graph of this function is going to be? So this is 0 0, this point is 1 0, this point is 2 0, this point is 3 0 and so on, this point is minus 1 0 and so on. So for all the values of x less than 1, this is the function here. Now since this function is continuous at x is equal to 1, when x is equal to 1, the value of the function is 1. This is the point here. for all x less than 1, when x is equal to 0, x is equal to 0, y is equal to 3. 1, 2, say this is 3 here. Join these two. Between 1 to 2, it is 1. Now, since it is continuous at x is equal to 2, so f of 2 is equal to 1. For all those values of x greater than or equal to 2, let us take x is equal to 3. 3 to the 6 minus 3, 3. When x is equal to 3, y is equal to 3. So this is going to be the graph of this function. Even looking at this, sorry, you can see that this function is continuous everywhere, and in particular it is continuous at x is equal to 1 and x is equal to 2. Now next is, for what value of lambda the function becomes continuous at x is equal to minus 1. For what value of lambda the function fx is equal to, that is your x square minus 2x minus 3 upon x plus 1 when x is not equal to minus 1, and is lambda when x is equal to minus 1. So for what value of lambda this function becomes continuous at x is equal to minus 1. When the statement is like this, that for what value of lambda this function becomes continuous, so which means that the limit of this function already exists. Limit exists, but for the value of lambda which we have to find, which will make this function continuous. So for continuity at x is equal to minus 1, we have limit x approaches to minus 1, fx, this must be equal to f of minus 1. Why we have written it this way and not the left hand limit and the right hand limit? Because it is obvious from the statement that the limit of this function always exists at the point minus 1. So this is equal to lambda. So limit x approaches to minus 1, what is that? X minus 3 into x plus 1 upon x plus 1, this is equal to lambda. Now applying the limit, minus 1 minus 3 is equal to lambda or is equal to minus 4. So which means that when lambda is equal to minus 4, then only you can say that this function is continuous at x is equal to minus 1. Now next is, for what value of k the function fx is equal to log of 1 plus ax minus log of 1 minus bx upon x when x is not equal to 0 and is k when x is equal to 0. So for what value of k we can make this function continuous? So the statement is, for what value of k the function fx becomes continuous. So once again we have to determine the value of k which is going to make this function continuous. That means that simply implies the limit of this function exists. Since the limit exists, so therefore for continuity limit x approaches to 0 fx, this must be equal to f of 0. So what do you mean by that? That is your limit x approaches to 0, it is log of 1 plus ax minus log of 1 minus bx upon x, this must be equal to k. Now as we know that limit x approaches to 0, log of 1 plus x upon x is equal to 1. So therefore limit x approaches to 0, log of 1 plus ax upon x minus limit x approaches to 0, log of 1 minus bx upon x, this is equal to k here. Now because here the coefficient of x is a, it is to be multiplied by, that is your limit x approaches to 0, log of 1 plus ax upon ax into a. Because in the second case the coefficient of x is minus b, so therefore log of 1 minus bx upon minus b into minus b, so this must be equal to k. While applying the limit, constant is to be taken outside the limiting sign, so this implies that a times limit x approaches to 0 log of 1 plus ax upon ax plus b times limit x approaches to, that is your 0 log of 1 minus bx upon minus bx is equal to k. So this implies that a plus b, this is equal to k. So that is, when k is equal to a plus b, then this function will become continuous at x is equal to, that is your 0 here. Now similarly the next question is, we have fx is equal to, this is 3ax plus b for x is greater than 1, it is 11 for x is equal to 1, and 5ax minus 2b for x is less than 1. Now it is given that is continuous at x is equal to 1, then we have to find a and b. Now because it is continuous, therefore limit x approaches to 1, positive fx is equal to f of 1 is equal to limit x approaches to 1, negative fx. So this implies that limit x approaches to 1, positive 3ax plus b is equal to 11, and limit x approaches to 1, negative 5ax minus 2b is equal to 11. So this implies that 3a plus b is equal to 11. This implies that 5a minus 2b is equal to 11. So solving these two equations simultaneously for a and b, and we will get the answer. So if you multiply first with 2, 6a plus 2b is equal to 22, 11a is equal to 33, implies a equals to 3. If we substitute the value of a here, so 3 into 3 plus b is equal to 11, so this implies that b is equal to 2. So that means if a is equal to 3 and b is equal to 2, then we can say that this function will become continuous at continuous at x is equal to 1 here. Now next is, if fx is equal to root 2 cos x minus 1 upon cot x minus 1 when x is not equal to pi by 4, then we have to find pi by f of pi by 4, so that function becomes continuous at x is equal to pi by 4. So we have to find, that is, find f of pi by 4 so that this function becomes continuous at x is equal to pi by 4. Now for continuity, limit x approaches to pi by 4 under root 2 cos x minus 1 upon cot x minus 1, so this must be equal to f of pi by 4. If you straightway apply the limit here, x approaches to pi by 4, you can see that it is root 2 into 1 over root 2 minus 1 over 1 minus 1, which is your 0.0 form. To remove this form, because only since this is 0.0 form, let us take x is equal to pi by 4 plus h. As x approaches to pi by 4, this implies, can I say that h approaches to 0? Because when you take x is equal to pi by 4 here, as x approaches